right? This is running on our deployment, and it's gonna use Matic. So we have two accounts here. There's one account here. It's account 1, F05, etc. And on the other side, we have a second account, CHC, etc. They both have plenty of Matic tokens to run. So first player is called Johnny B. It will be something's happening. He didn't like something. Don't know what. That will be cut out. Now there's something happening here. Let me see. Execution reverted. Player has already joined. That's what's happened. This guy's sorry. This guy is already in the game. So it wasn't the best demonstration because the guy had already joined before. I didn't know that. So when the other guy joins, both will probably make it there. So this is failing because he can't join the game again. He's already in the queue, waiting for the second player to join. So when the message is okay, I think it's coming. He joined. The other guy should be joining as well. There it is. So now they are both in the game. Join game 48, right? And so here come the shuffling parts. So start sending cryptographic initializations one side to the other. This is something that will improve a lot when we stop using MetaMask for all the interactions. Right now, everything that's being submitted from one side to the other is being submitted through the blockchain. And the user needs to sign the transaction using MetaMask. So this first thing we'll do is that this will the other guy now received the initial cryptographic information, and he's sending his key back. So there's a back and forth here, and we are going to implement Portis, which is another wallet, so that the user doesn't have to click every time for this back and forth, and this will make it a lot easier for people to have their experience there. Of course, we are also going to improve the speed of all of this. First this is the mock implementation, so this is not so slow, the back and forth. So here the DEX are being exchanged and encrypted. This is the mock version, so we can actually understand which card is which. But for the real version, this will be very encrypted and unintelligible. And then, of course, we have in the end the idea that we'll be exchanging this information through direct communication between the players instead of submitting through the blockchain every time, which is the final version, right? To have real fast initialization and exchange of information without having to submit every transaction to the blockchain. So Polygon is very fast. So now finally they exchanged all the encrypted DEX, and they also exchanged the decrypted cards here, which is one player is revealing the other player's cards. He has to send the cryptographic keys. So you know how this works, right? You have one user has shuffled the DEX and encrypted it, and then it sends it over to the other one who reshuffles it and re-encrypts everything. So now nobody knows which card is which. And the only way to review a card is both collaborate and send their keys. And in the case of the private cards, one user sends the keys to the other user. So user 2, Jack Star here, knows these cards, but I don't. Johnny B doesn't, because he doesn't have, Jack didn't send those keys over. So everybody has the keys for his own keys, and with the other guy's keys, you can see the cards, right? For the cards in the middle will be the flop cards, will be revealed later, and both will send their keys over so that both can see.
So in that way, we can preserve privacy over a public blockchain, which is very interesting.
Yeah, the thing is, there's some zero knowledge magic behind the scenes here for the real thing. But the basic idea is that what is exchanged through the blockchain is always encrypted. The private keys remain always on the user's devices, so they're never revealed unless the user needs or wants to reveal it. For instance, in the beginning of the game, it is required that one user reveals the cards of the opponent's cards, reveals the keys of the opponent's cards, so that he can play. If he fails to do so, that's invalid move, so to speak. That's something that's a misbehavior. And then the challenging process can happen, and he will be punished for that, right? So he needs to collaborate. So now we can call or do our bets here. So again, we are always interacting with MetaMask to do that. So it's Polygon, it's fast, but still takes a couple of seconds for the transaction to be effective in Polygon. So Polygon to there it is. Now this is a message from confirmation of the transaction. And then the listener on the other side just got it, and he can play as well. So if he checks now, this means that we go to the next phase of the game. We go to the flop phase of the game. And what happens now is that, again, here, there are lots of back and forth that we can optimize as well, because when I checked, I could already had sent the keys for the flop cards. But here, there are more backs and forths happening, could be optimized. So when this user here receives the notification that the other guy checked, so we can already, there it is. So he can deal the flop cards, you see? So he's sending the keys for the first 3 cards here on the table, which are the flop cards. And when he does so, the other guy will get those. He will already be, since he has the keys for those himself, so that his own keys, he will already be able to see it once the transaction is completed. It's completed, and now this listener, okay, he got it. He's going to deal the flop cards to the opponent now, so that both can see the cards on the table. There it goes. So he's on a flop already. He has the keys from the opponent. He already sent over his own keys. And when this guy gets the Jack Star's keys, there it is. He will see the same cards, right? So this is where you see that this is really the same game. They are exchange the decks are encrypted, and now that they've shown each other the keys, they can see the same cards there. And actually, this guy is really, really good, right? He has 3 aces, man.
Fantastic.
And he's not cheating. Well, there are 2 aces on the table, so that's not so hard. But
and
he's got an ace. He's gonna win.
That, and this is implemented.
Oh, no. This guy has almost a flush.
Oh,
this game is over.
Yeah. And Milton, this is implemented in our technology that if there's any attempt to invade the system and cheat, then the system will recognize this immediately and start a verification. How it works, this small part?
Yeah, so the thing is, you remember from the articles and the documentation, you have this poker engine which has all the logic and knows how to deal with all the cryptographic stuff. And the idea is that you have opponents, right? Players. So one is checking on the other. They have the same thing running on the browser. So if one guy makes a move, he has to send it over. The other guy will absorb that move and run it locally on his engine. If it's an invalid move, he did something like didn't reveal the cards, or didn't in the end when they're computing the results, one guy, they disagree on the result, who won, etc. So when this happens, one guy claims something and the other guy disagrees. At any point in the game, the one that found an error or a disagreement, he can go to the smart contract and challenge the game, as we say. So that's asking for the blockchain to verify the correct result. And this is where Cartesi comes in. So it triggers a Descartes computation. So the turn-based game contract, which is the one mediating between the players, receives this request for challenging the game, and he starts a Descartes computation. He goes to the Descartes smart contract, and he triggers the computation there. When that happens, the validator nodes, the Descartes validator nodes, also have the same poker engine that's running in the browser. It's running on this Descartes validation node. It's exactly the same code. And the thing is, all this data here that has been exchanged, it's been recorded on the blockchain. So it's available for these validator nodes to download and replay the entire game. So if one of the guys just didn't reveal us, like instead of sending the correct keys for these cards on the table, he sent something else so that the other guy can see what's on the table. And the other guy complains, well, the Descartes computation can run the same thing and see if the key is valid or not. And if the key is invalid, he'll say, okay, Jack Star here just sent an invalid key. He lost the game. He's going to be punished. Our default implementation is to simply take away all the tokens that the guy had and burn half and give half to the opponent.
And Milton, when you say the guys complain, is not the poker player himself or herself. It's
yeah,
actually...
no, it's the app itself that's running on each guy's device. So Jackstar, so this browser here, when he receives, it's all automatic, right? He receives the opponent's move, sends that to his own engine that's running inside here, and if the engine raises an exception or something like that, there's an error, then the app itself will call the challenge procedure on the smart contract. The user doesn't do anything. And actually, if the user would by himself simply, I want to challenge this game, he will be the one punished for asking for a useless challenge. If there's nothing wrong in the game and somebody, because you could write your own code here, your JavaScript code, you could change the app and just ask for a challenge for no reason. But the verification machine, the verification that's running inside Descartes, it's coded in a way that he'll run the entire game. If the game has finished, he will check the result and see what the guy claimed and what the other guy complained about, and see who's right and who's wrong. If the game hasn't finished yet, okay, if there's an illegal move, then the guy that did the illegal move will be punished. But if the game hasn't finished yet, there's no illegal move, everything is fine, well, the guy that just asked for the verification, he's the one who get punished, right? But this is very flexible. You can write the logic that you want, but the idea that we are putting for the game for the real game to go forward is this: anybody who does something wrong will be punished, because the idea is that you only have to go to verification, spend resources and ether and everything more than you needed to, is to be punished, so that things can flow, because the verification takes a couple of minutes to run, right? So it's something that people should avoid if it's not a necessity, right?
Milton, can we go to the turn? I'm just curious to see
Sure.
how the rest unfolds.
Right. So I'm gonna raise here because I think I'm gonna win. I have no idea that guy has a flush, almost a flush. So I'm gonna raise here quite a bit, actually. Raise by 100. I send it over to MetaMask.
Because this is running on a Polygon test network, correct?
Yeah, exactly.
Yeah. Okay.
Yes. He got the raise, and he's gonna call because he thinks he has a chance, right?
Yeah, absolutely.
Right, he called, and now this is the thing that we can still optimize, right? He could already have called and sent the keys for the turn card in the same package, one transaction. But here we are unoptimized, so he sent it over. When Johnny here receives the fact that he calls, so now he's dealing the turn card. So only now will he send the keys over, and when Jack here receives that, he'll return his own keys for the turn card so that both can see what's on the table for the turn card.
Okay.
And if it's clubs, then Jack will be happy. Let's see what happens. A couple of seconds until the listener gets the transaction. There it is. Confirm. So what's the card? What's the card? Ah, it's not club. It's not club. So it's still good for Johnny here. You want to go all the way to the end?
Yeah, it is good to river, yeah.
John is gonna raise it again. More 100.
And,
easy peasy.
And Milton, while is flowing the cards, the poker is written on C++, correct?
Yeah.
So beside of the flexibility on the language that you choose to implement and the massive computation scalability that our technology provides,
I'm gonna call again.
When we're gonna see this amazing demo technology showcase becoming a product, how do you see that?
Yeah, so this is a showcase, right? We wanted to show that it's possible to do something like this, because the cryptography involved here is really, really complex, and there's no way we're going to write this from scratch. He's gonna deal the river card now. So the thing is, there are libraries out there. The thing with all this cryptography, which is called mental poker, right? It's pretty complex, and it's a lot of academic research actually involved there. And there are libraries written in C++ that run on Linux, etc., that we are using. And actually, they are very. It's not clubs. He lost. Poor guy. The thing is, we can take advantage of software that's ready, and that's one big advantage. We could choose other languages, of course, but in this case, it's complex, it's resource intensive, computationally speaking. So in these cases, you really want to have a compiled language, which is more efficient, like C++ in this case. But depending on the complexity, I'm gonna just check here. Depending on the complexity of the game, of the logic, if it's reasonably complex but not so much, maybe you could go to some interpreted language like Python or JavaScript even, and you could use that. So we had an example in the repository, and there's one article that explains how I use the same infrastructure, which is this back and forth using the smart contract to play chess. I don't have a user interface for that, but it was really fast to just download chess.js from npm, test it using Node.js, and then run it inside a Cathedral machine, which also has a JavaScript interpreter. And it's there. And then we write the logic, and okay, if this move is invalid or not, then so this is the nice thing. So there's a number of aspects, right? It's faster to code because you can use something that's already there. You don't have to code from scratch. You can run things that were impossible to run on layer 1 or even most layer 2, because we have the RISC-V architecture we have is more efficient than the EVM in general. And we are something that's sometimes counterintuitive. People think that the EVM is safer, but depends on the contract, right? If the contract is broken, then it's broken. And if you are using battle tested software, it's safer than using very complex contract that nobody has ever executed before, and so it could be lots of security holes in there. So this is where we think we can, and for this to become a product, there's still some things to do, right? We need to do these optimizations. We need to do some direct communication between the players and finalize some integrations to have it all working.
But the moment that I won, there's no central authority that I wire the money to. So actually, the moment that I won, almost immediately, it's in my wallet.
Yeah, it's in the wallet right now. It's in the guy's wallet again. So if he exits here, so this is the poker tokens that he has in his wallet. He won. He had 1,000 or something, right? Now he's got. I know he had a little more. He earned some 2,000 poker tokens here. 200, sorry. And this guy lost his. But this is already the poker tokens that he has on Matic testnet on his wallet. This is not something that's inside Cartesio or somewhere else, right? If there was a verification, so this is how these contracts are working right now. When you join the game, you send your tokens over, and they are locked in the game. So when the game finishes, they are given back more or less your bets, right? So if you bet something and you lost, then you get only the remaining part back. If you cheated, you lose it all. But the moment that the game ends, so be it by normal means, or be it by somebody misbehaved and there's a verification, by the end of the verification, then you can get your tokens back. Yeah. But that's it. When the game ends, tokens are there.
Yeah. And Claudio, what will be the next thing that you will be working on from here then? So what is then the next move?
Yeah, we are working in these polishment features that Milton mentioned to enhance our UX experience and performance. These are the two main features that we are focused on now to have a better experience in new UX and performance. That will bring a lot of difference for the experience in the game.
Awesome. A lot of work, but awesome. Yeah, but it looks already quite nice, you know?
But now it's becoming funny work because we can play.
Yeah.
Finally we can play. Super nice. Claudio, can you maybe explain something about the wallet and how that works? Because we've seen that immediately the coins are transferred, but how does that work with the wallet then? Because we've just seen it in MetaMask.
Yeah, we have currently our solution is using MetaMask. That's a very popular solution, but for our game, as you've seen in the video, we have many transactions occurring. So MetaMask is always asking for confirmation on each transaction, and that for the user experience can be annoying. So we decided to study an alternative solution called Portis. That's a non-custodial solution, also as MetaMask. And this in Portis, we can control the asking for confirmation for the users, and then we can programmatically omit some of these askings, and then we can have a more fluid experience for the user, and we continue having a wallet.
Very nice. Milton, any other optimizations that we can maybe expect, or are you working on?
Yeah. So aside from for the interactions, there is that I already mentioned, that we are doing a little bit more transactions than we actually need to. We can send more than one information per transaction, so to minimize that, right? Other than that, the main thing is that we are finalizing the integration, right, for the real cryptography, and it is we had first for ease of use and etc. We had focused on a web application, but for the real thing, it will be a little bit annoying for people to use because it will take a little long for especially the shuffling and encryption, which uses zero knowledge proofs and takes a while to run. So, and we found out that most poker solutions actually use desktop software, so the user actually installs. This was something that we were previously thinking that people would like to have for better onboarding, don't have to install something, that we would be maybe suspicious of installing something, but actually that's very common. All the poker solutions install software. So we are probably going to move this to something like Electron, which can run this same thing, but using as the back end, instead of running the poker engine in WebAssembly, which runs in the browser, we'll use native code, which runs basically fast, and this will be instantaneous and will be together with Portis or some other non-custodial solution that minimizes interactions for submitting the transactions. This will be like really, really nice solution. You have fast interactions and without bothering the guy too much. So I think this will be already pretty nice. The only thing then for a complete product would be the thing that for simplicity, we are exchanging information always through the blockchain, and we'll probably look into some more direct communication between the players so that they only go to the blockchain if there's disagreement and disputes. That will require some signing of messages, something like that. But so most immediately, we want a non-custodial wallet without user interaction all the time, and this more efficient desktop solution.
Nice. I can't wait.
We're getting there. We're getting there.
So good. Bruno, do you have any things before we round off?
No, I think it's great. We have a great overview about our poker demo, and I'm starting to see the next steps.
Yeah, awesome. All right, thank you so much, guys, for today, and yeah, let's see each other next week.
All right.
All right.
All right. Thank you. Bye-bye.
Thank you, guys.